How does photon loss affect photonic qubit errors? Imagine sending a message through a busy city street, and some of the letters just vanish before reaching the receiver. That's similar to what happens with photon loss in quantum computing. Photonic qubits are quantum bits encoded in particles of light, like single photons. These photons carry quantum information through optical fibers or waveguides. But sometimes, due to absorption, scattering, or imperfect transmission, photons get lost along the way. When that happens, the information they carry can disappear or become corrupted. Photon loss is one of the main sources of errors in photonic quantum computers. When a photon is lost, it's like the qubit itself has vanished. This is called an erasure error because the system knows that the photon is missing. This loss can happen at many points, like in the optical fibers, beam splitters, or detectors. It reduces the chance that the quantum operation will succeed because the qubit simply isn't there anymore. In some cases, photon loss can cause phase flip errors. This means the relative phase between quantum states gets altered, which can mess up the information stored in the qubit. It's like the message gets scrambled because part of the original light signal is gone. Additionally, when photons are lost, the amplitude of the quantum state diminishes. This weakens the signal and makes it more vulnerable to noise, which can introduce further errors. To combat these issues, scientists have developed special error correction methods. These codes encode a logical qubit into multiple physical photons. If one photon gets lost, the system can detect it and recover the original information. For example, some experiments have shown that even if a single photon is lost, the quantum information can be restored using measurement and correction techniques. Another technique involves nondestructive photon detection. This allows the system to confirm whether a photon is present without destroying its quantum state. It's like checking if a letter is in the mailbox without opening it. This method helps improve the fidelity of quantum operations despite photon loss. Some architectures use entangled resource states, like Greenberger-Horne-Zeilinger states, to help detect and correct photon loss errors. These states are highly correlated, so if a photon is lost, the system can identify the error and fix it. This approach pushes the threshold for fault-tolerant quantum computing higher, making photonic systems more reliable. In real-world setups, photon loss accumulates as light travels through different optical components. Losses from couplers, waveguides, and detectors multiply, reducing the overall success rate of quantum operations. That's why optimizing hardware to minimize loss is so important. Using high-quality components and efficient detectors helps keep photon loss low. In summary, photon loss causes errors by removing the photons that carry quantum information. This leads to erasure errors and phase errors that can degrade the entire computation. To keep photonic quantum computers working well, researchers use a combination of hardware improvements, nondestructive detection, and specialized error correction codes. These strategies help recover lost photons and maintain the integrity of quantum information, paving the way for more dependable photonic quantum systems.